Greetings, everyone. This is Bobby Vaughn Jr. with a call to actions. Today is a very special day as we have the one and only Dr. Chris Busby, one of the foremost scientists on the topics of radiation and how it affects the human body. He considers himself one of the last of the Mohicans in this. He's traveled all across the planet studying the effects of radiation on people. And it's an honor to have Dr. Chris Busby here today. Dr. Chris, thank you. Thank you for being here.
Yeah. I'm grateful to you for asking me. I'm one of the last of the Mohicans. What that means is that, you see, there were a lot of very, very clever and eminent scientists in the last 30 years, maybe 40 years, who opposed the risk model of that has been used since the development of nuclear weapons to estimate the health effects of radionuclides, of all the radioactive contamination that gets pumped out of places like Chernobyl and Fukushima and all the big sites for production of weapons material in the United States and elsewhere. These are people like Alice Stewart and Rosalie Bertell and Alexei Yablokov and Carl Morgan, Ernest Sternglass, a lot of people. I knew all of them. I knew them all, and now they're all dead. So it's only myself and Inga Smitsfeuer-Harker, perhaps, I suppose, out of that gang that are still alive. Because they were all older than me, and I'm getting old now too. So I see myself as the last of the Mohicans, but I would quite like to get some little younger Mohicans, if you like, to come along and do this sort of thing. But it's very difficult for young people to work in this area because there's no money in it, you see. So that's the sense in which I'm the last of the Mohicans.
Yeah, and one issue that we're facing is that the younger generations would rather just play video games rather than take on the most important situations that Earth's ever had to deal with. And we definitely need to get the young generations interested somehow, because that is very important. And just to go into some of the questions, I have a few questions, but I pretty much want to keep this a conversation, not well scripted. But there's definitely one question, speaking of the younger generations, that I have, is how many generations, according to what what you've studied as a scientist in this field, how many generations does the effects of radiation affect children?
Yes, well, that is a good question. We know from the work that I did on the nuclear test veterans. These are people who were exposed in Christmas Island in the Pacific when they were first developing the British bombs. I've studied their children and their grandchildren, and we know that the effects, the genetic effects in the children, which are about 10 times the expected number, so they're about 10 times more genetic defects, birth defects in the children of the test veterans who were born when they came back from because these were all national servicemen, young men, so they were born in the 60s. Their children also, so we've got two generations there. Their children also have almost the same level of genetic damage, which was quite unexpected, because if you consider this as a direct genetic effect, you would expect it to just go down, 1 quarter, one half, 1 quarter, 1/8, 1/16, and so on.
Right.
It's in some Mendelian way, but it doesn't. It sort of continues at almost the same level, and we know why that is now. It's a process called genomic instability. So, if that trigger is switched, if you like, then what happens is that the genes then just get scrambled in the generations going forward from the person that was exposed. Now, in the Chernobyl affected territories, there was a big study by a geneticist who worked with us called Rose Goncharova, and she studied her team studied mice, or what they call bank voles, which is just a small rodent lives there, and they found that these effects continued for 22 generations. So it doesn't look good.
No, that does not. 22 generations, because the last I had heard, radiation affected human beings for 4 generations. Does that seem a little low to you?
Well, I'm not quite sure where that came from, but I mean, it may be that it came from a study that only had studied 4 generations.
Right.
Because after the human generation is 25 years, and radiation's really only been around in the sense that it's been contaminating people and so forth since 1910 or 1920. When all these radium and uranium started to be spread all over the place. Then, of course, it really took off in the 1950s. So you've only had 4 generations anyway. But certainly, there's no reason, it seems to me, why we wouldn't respond in the same way as the rodents do. So what will happen, of course, is that people who carry this signal, this genomic signal, will carry it through all of the generations until their offspring die out without issue. I think that's how it works. So that's the only way that this genetic signal will get out of the human gene pool.
That's a great point. I've never heard that before. Is that we have not been able to study the generations of the ones who have been affected because, it's only been around for about a century now. And
well, the reason they could do the mice, of course, is because the mice breed quite quickly, and you can get babies like every year. But with human beings, you can't do that. You have to wait significant time.
Right, and more than likely, scientists would be like, okay, let's create a computer system that could simulate it, but definitely the computer system would not be as accurate as if we actually physically studied the effects.
Well, I wouldn't trust the computer system anyway, frankly. It's of course the whole point about that sort of mathematical approach is garbage in equals, and garbage out. And a lot of the pickle that we got ourselves into over this whole business of radiation is because physicists have tried to reduce the concepts down to very simple levels that they can apply mathematics to. But human beings, living bodies are not like that. They don't work like that. They're much more sophisticated. They have really complicated intervention systems, like genetic repair mechanisms and all sorts of things. So, and in fact, it seems that in the way in which human beings are affected is it's not so much that the genes are affected directly. It's just the way in which it works is the repair system is affected. That's how it works. So it's not at all what would be expected. The original risk model, the one that I attack, the one that I say is a load of nonsense, and the one that reality, that empirical studies show is a load of nonsense. That risk model is very, very simplistic. All it does is it assumes human beings are like a bag of water, and it dilutes the energy from the radioactive decay into the bag of water. And then what it does is it says, oh, well, this is your dose. And then on the basis of your dose, it equates external radiation with internal radiation. But it's quite ridiculous, because internal radionuclides are chemicals. They're all these different chemicals, and they have different chemical effects and biochemical affinities and so forth, depending upon what chemical, what atom, what element they are. This is particularly true of uranium, because uranium has a very strong affinity for DNA. So it goes directly to the DNA and sticks on it, and then it decays and smashes the DNA up.
Yeah, I'd like to get into the discussion of plutonium and how it's both a radiological poison and a chemical poison. But before that, what are the effects on chromosomes and DNA that lead to mutations? How does radiation create mutations in the human body?
Well, what happens is that when radiation impact, when external radiation, gamma radiation and X-rays, when those impact on the body, what they do is they break a chemical bond. The energy is absorbed by a molecule, and then that produces a fast electron. So all the effects of radiation are ultimately a consequence of ionization due to tracks of fast electrons. So these electrons are like whizzing through tissue, and as they hit things, they bounce off them, and energy is absorbed and breaks. A bond is broken, and you get what's called an ion, which is you can think of it as like a little hot particle, a little dangerous hot reactive particle, or molecular fragment mainly. And most of these molecular fragments are fragments of water. So water is H2O, but when it gets hit by an electron, it becomes OH and then H, or OH dot, or HOHO. There are a lot of these little hot species. Now what they do is they then float about the place and quite quickly react with something that's next to them, because they're extremely reactive. Now if what is next to them is DNA, they react with the DNA. So they attack one of the bases or on the DNA spiral, and there are these different bases that make up DNA: adenine, guanine, cytosine, those things. And it is these molecules that bind together and form the backbone of DNA, which are the genes. That's where the genes are. Now if you bust up one of these things, if you react it to one of these hot water species, or even if you hit it directly with a fast electron, it changes its nature, changes its chemical nature, and the bond can break. So then, in fact, the DNA molecule can just crack open, and especially true for alpha decays from internal alpha emitters like plutonium and uranium, because the alpha particle is very, very much more strongly ionizing than a fast electron. And what that does is it can cut through both of the strands of the DNA. Now the thing is, if you cut one strand of the DNA, what happens is it then gets repaired, because these are complementary strands. So if you like, there's a message written on one strand, and the complementary message is written on the other strand. So it's possible to copy the correct answer back and repair it. But if you break both of them, if you have a really powerful hit, or a track from an alpha particle or a neutron that goes through there, it'll crack both of the strands of the DNA, and then there's no way in which it knows how to repair itself. So under those circumstances, you get a DNA mutation. You can still get a DNA mutation if the copying goes wrong. That's another way too. So, for instance, when the copying mechanism comes along and tries to repair the DNA, and it can't do that properly, you get a misrepair, and so that's also a mutation. So it's those mutations that lead to problems. Of course, they're not all likely to go to cancer. I mean, some mutations will just not affect the system at all, because they'll be irrelevant. They'll be a part of the DNA that doesn't have any useful message to say. But other ones will cause the cell to just die. And that doesn't matter either, of course, because the dead cell doesn't go on to become cancer, although it will affect the integrity of the body, and it might affect general process, so it might make you ill, but it won't go to cancer. But if you get the right sort of mutation, or I suppose I would say the wrong sort of mutation, then that can go on to form to initiate cancer. Of course, it doesn't necessarily initiate cancer. It initiates a precancerous process, which can then be picked up by the immune system and knocked on the head. This sort of thing happens all the time. But if it's not knocked on the head, then you get a tumor, and then you're in trouble. And the other thing that can happen, of course, if it's in a germ cell, then you pass this genetic mutation onto your child, onto the fetus, through the sperm, through the egg, and then the child can die in the womb, or can come out with a congenital malformation, or can later on develop cancer. So those are the general downstream issues.
Germline. Yeah, I didn't know about the germline. That seems pretty common in these cities where these nuclear sites reside.
Oh yes, that's right. I mean, that's true. In fact, United States, because the United States was preeminently the developer of these weapons. There are all these sites in the United States, like Hanford and Fernald and Rocky Flats and Portsmouth, all over the United States. They're places where they developed the materials for making the nuclear weapons. Lawrence Livermore. They release this stuff to the environment. So all of these areas are extremely contaminated, and the contamination flies all over the place in the form of small particles of uranium or plutonium or various other downstream daughters of the uranium 235 and 238 series, and there are a whole load of those. And a lot of them are alpha emitters, and they just get inhaled by people living nearby, and so you've got cancer clusters and congenital malformation clusters near nearly all of these sites, and also near all of the nuclear sites where they have where they make nuclear power stations where they make electricity. Those sites are also surrounded by people who are sick, who have a higher rate of cancer. I've studied a number of nuclear sites, looked epidemiologically, and looked at levels of cancer near 3 nuclear sites in Britain, Hinkley Point, Bradwell, and Travis Bennett. And in all 3 of them, we found statistically significant excess risks of breast cancer in the women living nearby over periods of time. And this was using official data from the British government, from the Office for National Statistics. Or in one case, we went in and we did a questionnaire study with the BBC, with the Channel 4 in Wales, S4C. Mm-hmm. And so in all of these cases, we found significant serious health effects in people living near these nuclear sites, and it's certainly also true in the United States. But we're not. We find it's very hard to study them in the States because they won't give you the data. The cancer registries won't release the data to small areas, so it's quite hard to do.
You gotta force it out of them, and it's kind of sad because it's been a massive industry for going on 100 years, or maybe even over 100 years now. And when we try to find the evidence on what's happening, say in a certain field or a certain line of nuclear research and development or testing, we have to pretty much pull it out of them, force them to give it to us. Thank goodness.
That's right. Well, they won't give it to you. I mean, I've never known yet anyone, certainly in my country or in the United States, I have not been able to find anyone who's been able to extract cancer data to small areas out of the cancer registries. We're going to have a go. I'm involved in a number of court cases in America, and we're going to have a go. But I'm not. Mm-hmm. I'm not sanguine about the result of all of this. But there is a way around. I mean, it was the way that I developed for examining the cancer risk near a nuclear power station in the United Kingdom, and that you just go and knock on doors. It's really quite simple, and it really freaks out the people who are trying to hold onto this data. Because see, the other thing about cancer registry data is that you don't know that they're not lying. I mean, you say, how many children here with brain tumors? And they say, 4. But I mean, they could say anything they like. They could say 2 or 6 or whatever they wanted, or none. And you wouldn't know whether it was right or wrong. Whereas if you go and knock on somebody's door and you say, excuse me, in the last 5 years, has anybody here suffered from cancer? What sort of cancer? How old were they? And all the rest of it. And you also ask them how many people lived there and how old they are. Then you get a base population that tells you how many cancers you would expect in that base population. And then you look to see how many you've got. It's really simple. It's a fantastically simple method. Anybody can do it. You just go and knock on doors, and it takes about a couple of weeks. You get an area of about, 500 houses, something like that. That gives you a statistically significant result, and that's all you need to do. I'm amazed that nobody does it. Anyway, I've done a few of those, and I wouldn't mind doing some in the United States.
We would love you to do some of those in the United States, and I think, wink, wink, what cities to look at the beginning of the uranium process. That's pretty much all I could say. Yes.
Well, one of the problems I have with all of this is actually I don't like being in the United States. I don't want to sort of put it down or anything, but I find it rather a scary, creepy place, I mean, never used to. I've been here lots and lots of times, but it's getting worse and worse, and it's getting more and more insulated and isolated globally. And then, of course, you've got a mad president as well. But it's not only the United States. I have to say that England also is going off its head at the moment. So I'm not sure that I want to be either in the United States or England. I think I'm going to go and live up in the frozen north for a bit and just hide out.
Yeah, well, both the U.S. and UK need to come together and listen to a lot of Sex Pistols together, and have a little party. But it's so important that we, as a younger generation, to get this information. Going back here, we talked about the chemical poisoning, how when radionuclides enter the human body, they become a chemical poison. What about plutonium as it being, is it the most poisonous poison that has ever existed on this planet?
No. I don't. Somebody said that once, and it seems to have become something that's repeated again and again and again.
Right.
The important thing, and there is a subtle point here, but it's a very important one, and that is that the actual quantity of material that you get from a radionuclide that is quite radioactive, like plutonium, is extremely small. It's sort of absolutely vanishingly small. And so if you got something like plutonium at the level that would probably kill you in terms of its radioactivity, the amount of the chemical amount of that you would have is so small that it would have no effect at all. I mean, if you imagine that there's a kind of plutonium that doesn't have any radioactivity, then you took the same amount of that plutonium and you put it into the body as the same amount that would kill you of the stuff that did have the radioactivity. Your body wouldn't even notice. The concentrations are tiny; they're like nanograms, micrograms, that kind of thing. And it has a certain toxicity as a chemical, of course, but that's not the point. The toxicity is due to its radioactivity. And plutonium also binds to DNA, incidentally, like uranium. And this, if you like, is one of the most important things about uranium, is it has this affinity for DNA. But of course, in the case of uranium, the amount that's associated with the amount of radioactivity that would kill you is a great deal, because it's a very weakly radioactive substance. It's got an enormously long half-life, about 4.5 billion years. And so, in fact, the amount of radioactivity necessary to harm you is in fact associated with quite a lot of uranium. Mm-hmm. So you'd have to sort of have a teaspoonful or something like that to get ill, and that of course is quite toxic, because uranium is quite toxic anyway.
Yeah, even outside of the realm of plutonium and transuranics and fission products, but I do want to touch on some fission products.
If you take the famous fission products, are cesium. I mean, these are the longer-lived ones. Are cesium-137 and strontium-90. Okay. Yeah. Now, the kind of dose that would kill you from cesium-137 is associated with such a small amount of cesium as a powder that you barely see it. I mean, if you take all of the cesium-137 that came out of Fukushima, like the whole lot. Yeah, all of it. Yeah. So about 10 to the 17 becquerels, right? That's 1 and 17 noughts becquerels. It's only 1 kilogram. You could put it in a paper bag. That's what you've got to realize, is that these radionuclides, there's not very much of them. You don't need much of this stuff to get a huge kick. A huge sort of dose out of them in terms of.
Even in the realm of uranium, I think anyone who's done any research, they understand that uranium is the beginning process of creating all these other radionuclides. These individuals may actually take their sights off of still the radioactivity of certain uranium isotopes, and living in these cities that process uranium. These families are exposed on a just beyond comprehension level to these radionuclides from uranium, living like directly across the street.
there's a lot of uranium, and uranium also, as it gets out of these plants, gets out in much the same way as depleted uranium goes around in battlefields. I mean, and I have done a lot of work studying the health effects of depleted uranium in Iraq and Kosovo and the Balkans, and what you have coming out of the uranium sites like Paducah and what's the other one? Portsmouth and so on. Those levels of uranium are extremely dangerous, and I'll tell you why why this is. It's been completely overlooked. It's been overlooked because the risk model, the radiation risk model that's current, the one that they use in order to say it's safe, that one just dilutes the energy from the uranium into a bag of water. And the energy from uranium when it decays is not very large, because it's quite a weak alpha emitter. But the point is that the quantity of uranium that comes out of these places is such that as a chemical, if you like, it gets into the body and then it binds to DNA. It goes into it follows the calcium into bone as well. But it also binds to the DNA strongly. It has a very strong affinity for DNA. Now, I discovered, and this is kind of my thing really, that uranium has this strange ability to block gamma radiation. Just like lead, the absorption of elements is proportional to the fourth power of the atomic number. Now, the atomic number, as you know, hydrogen 1 and helium 2, lithium, and so on, all the way up. If you imagine the periodic table, the big heavy elements like lead and gold and platinum and so on are down in the bottom right-hand corner. And uranium is the highest atomic number of all. It's got an atomic number of 92. So the uranium's ability to absorb background radiation, and we're all exposed to this gamma radiation, background radiation, its ability to do that is proportional to the fourth power of 92 compared to the fourth power of oxygen, which is the main component of water, which is the main thing in the body, you see. So what happens is that uranium is the key absorber. If it's in your body, it's the key absorber of background radiation. Normally, background gamma radiation goes right through you. It leaves a little bit of a dose behind, but it goes right through you. But not if you've got uranium there. If you've got uranium there, that absorbs the X-ray, it absorbs the gamma ray, and it then turns it into a photoelectron. So just like a lead apron absorbs X-rays, a uranium apron absorbs X-rays and gamma rays also. And then the energy is turned into a photoelectron. Now the point is that the uranium is stuck on the DNA. You see, this is the strange, confluence of problems, that it's stuck on the DNA. It's sort of focusing the background radiation directly into the DNA as photoelectrons. So it's horrifyingly dangerous. And when you look see its effects in countries where it's been used, DU, you find these horrifying effects. I mean, the study we did in Fallujah, Iraq, where we showed that the uranium was there because we measured it in the hair of the mothers of the children with congenital malformations, we found a 35-fold excess of leukemia in the young people up to the age of 30. I mean, these are numbers, unbelievable numbers. In fact, nobody believed us because they said that they were too big, but that's what we found. It was a similar sort of thing to what you find if you go around these nuclear sites where they process uranium and it all gets, through the fence and it floats about the place and people inhale it. The levels of cancer around sites like the uranium processing sites is astronomical, and of course everybody knows there. I mean, if you go and talk to those people, every second person's dying of cancer, young people too. But nobody does anything about it because they say, oh well, it can't be the uranium because the dose is too low. It's monstrous.
Yeah, we need to talk personally on a few things outside of this interview, but let's just get to a question. What is, just in case anyone is wondering, what are the differences, or maybe just difference, between transuranics, daughter products, and fission products?
Well, yes, okay. Well, that's rather a difficult question to the differences are in their definition. So let's start with fission products. Let's start with uranium. Okay.
Mm-hmm.
I mean, it was first discovered that the fission of uranium was first figured out in the late 1930s, and it was actually effected when uranium-235 was created by its extraction from natural uranium from Belgium or from the Belgian Congo. It's brought to America, and a number of scientists who figured out that if you managed to extract it, you could get something that would make a bomb, a very big bomb, E equals mc squared, huge amounts of energy. So you needed a certain amount of enriched of U-235, the fissile part isotope of the uranium mixture. Natural uranium consists of uranium-238, uranium-235, and uranium-234. The uranium-235 one, if you get enough of it together, will create enough neutrons to form a chain reaction, and there'll be an enormous bang, and the 235 will split in half. So that's called atomic fission, and that was the basis of the first atomic bomb. Okay. So when it does that, it splits the U-235 in half, and when you do that, you get a lot of very reactive fission products, different elements like strontium-90, cesium-137, ruthenium-106. There's a whole load of them. It's all like the little bits of the uranium that you've blown apart, and those are the fission products. Now, when you first blow them apart, most of the fission products, and there's a whole list of them, are very, very reactive and very, very radioactive. That is, but they decay very quickly. So in about 3 weeks, they're mostly gone. Then you get some medium-length ones, which take a little bit longer. Then you get the slightly longer-lived ones, the two main ones of which are strontium-90 and cesium-137. So those are the fission products. So if you blow up a bomb, you get all these fission products, and because they're so radioactive, they're really quite lethal. So if you're out there and you've got all the fallout coming down, and you inhale some of it, or it falls on your skin or whatever, you get very, very ill, and you can die, as lots of people did at Hiroshima and Nagasaki as a result of exposure to fission products. Okay, where are we? Transuranics. Well, transuranics are just artificial elements which are created as a result of very large amounts of high neutron flux in nuclear reactions. So like when you have our uranium bomb and it goes off bang, it produces lots and lots of neutrons. That's how it works. And the neutrons then interact with all the various bits and pieces of uranium that are there, and they can push the atomic number up higher and higher and higher. So naturally, the only chemical element that's around on Earth, the highest atomic number chemical element on Earth is uranium, which is 92. But you can push it up 93, 94, 95, 96, and so on, all the way up to over 100, and create new elements like this. And those elements are called transuranics, and one of them is plutonium, and this is produced in a nuclear reaction in a nuclear reactor. So, and the other one is americium-241, which can be made in quite large amounts, and which you put into smoke detectors. It's useful in smoke detectors because it's a pure alpha emitter. Yeah. And its daughter is neptunium-237, which is another transuranic, and so on. So you've got these transuranic elements like neptunium and europium, and I'm not sure if that is one actually, fermium, dysprosium, americium, francium. There's a whole load of them anyway. And they're made in rather small quantities usually. They are artificial elements. They're created by man as a result of bombarding uranium and various other transuranics with neutrons. And these neutrons are produced in very large amounts inside these nuclear reactions. So there we are. We have the transuranics that are formed by bombarding uranium and other transuranics with neutrons, and then the fission of uranium-235 or plutonium, and their number. I mean, neptunium is fissionable as well. So when they've split in half, they create a whole shower of little smaller elements, which are the fission products, and those ones are very, very dangerous and radioactive. By and large, the transuranics are alpha emitters, so they produce alpha particles, which are charged helium nuclei. And when they decay by an alpha emission, they change their atomic number by 4. So when americium-241 decays with an alpha emission, it decays to neptunium-237. So you just take the number 4 off 241, and you get the atomic weight of the result. I mean, that's a sort of brief outline of it all.
Yeah. One thing that I've personally seen a lot of is from data is evidence of uranium isotope 234. And as in just normal uranium, of course, 3 isotopes: the U-234, 235, 238, and 238 being the most plentiful, but 234 comes in second. But isn't uranium-234 about 10,000 times more radioactive than the isotope 235?
It is more reactive, yes. The way you have to think about it as a series. 235 is a different series to the 238. 234 is a decay product of 238. So if you take the 238 series, starts off with 238, and then that decays to protoactinium-234 and thorium-234. Mm-hmm. So that's the first decay. It gives off an alpha particle. It decays to is 238. So it gives off an alpha particle. So you've got to take 4 off. So then it goes down to thorium-234, and then that decays to protoactinium-234. And both of those are beta emitters, and then that decays to uranium-234. Now, uranium-234 has a shorter half-life than uranium-238, so it's much more radioactive. But the amount of it there is only the same as the amount of in terms of its activity. The decay of the U-238 results in a single atom of U-234. So one U-238 decays and produces one atom of U-234. And then the U-234 then decays with an alpha emission to thorium-230. So you take 4 off again, and you go down to 230. Thorium-230 is a very nasty alpha emitter. You take 4 off that, and you go down to radium-226. And then radium-226 decays to produce radon-222. That's also another alpha emitter. And then radon-222 decays down to, there's a whole series: bismuth-214, lead-214, so on, all the way down to lead-206, which is stable. So this is the U-238 series. Then the U-235 series is a completely different series. So 235 decays down to 231, and we go on like that down there. So there's a whole other load of decay products there. I think what you're thinking of is this, or what you might be thinking of is this: that when you extract uranium-235 from the mix, from the ore, so you get the ore and you get a mixture of 238 and 235, and the 235 is a very small amount, a few percent, 0.3% or something. And so you've got to get it out. So you do that by using some method like a centrifuge or some method that relies upon, or gaseous diffusion or something that relies upon the atomic weight of these 2 isotopes. So the lighter one goes one way and the heavier one goes the other way. Of course, the point is that since you've got one activity of 234 for every activity of 238, and that 234 goes through with the 235, you see. So when you get your 235 for your enriched uranium, it contains about 20 times more of 234. And so this this was pointed out long ago with regard to fallout, because Carl Morgan was one of the Mohicans, one of the dead Mohicans. He came along to Aldermaston in England, and as a result of the court cases I was doing, we found a secret memo. We found a secret document that was a minutes of a meeting that he had at Aldermaston with British scientists, and he told them then that one of the most serious hazards on the battlefield, on the post-nuclear battlefield or on the test sites after they'd blown these bombs up, was U-234. So nobody had thought about that.
Yeah.
But the reason for that was that there's an awful lot of U-234 there that's mixed in with the 235 that they were using to make the bombs. And 234 has some quite seriously heavy alpha emissions. So it is a dangerous overlooked hazard.
Yeah. Thank you for going into depth on that. Highly appreciated. On the 238 now, and it's probably the same way in the UK. We have a massive stockpile of just leftover depleted uranium in the United States, just sitting, chilling at nuclear sites that have been decommissioned. That troubles me, first of all, because they're just stacked, in my opinion, irresponsibly, but according to NRC and EPA, they're stacked according to guidelines. A massive amount of uranium-238, which raises a question to me. That amount of U-238, could it affect the environment and the people around? And is it possible that Transuranics could be created in these cylinders?
Right. Okay, good question. I mean, the answer is that it is just about possible that very, very small amounts of fission could take place, and you'd get a very small amount of transuranics. I don't think that's the main problem. I think the main problem is that if this stuff got out, if the uranium got out, and then it would be an astronomically awful health hazard. And so some very, very serious attention should be directed towards finding a way of ensuring that it can't possibly get out. I mean, I've seen these casks that contain the depleted uranium, and a lot of them look like some ancient rusty sort of thing that from 1920s.
Yeah.
And of course it's jolly corrosive because it's very radioactive apart from anything else. And we know that if you subject metal to high levels of radiation, they corrode. I mean, it's not as if you're wondering about just ordinarily sitting there and rusting like your car might sit in the road and rust. These things are going to rust or going to corrode much faster because they've got uranium inside them. And in the case of uranium hexafluoride, you've got fluorine as well, you see. Mm-hmm. So you've got some extraordinarily corrosive materials. And they're stuck inside, and these canisters are so large. There's several tons of this stuff inside it, 20 tons or something in each canister. And then if that sort of corroded and the stuff got out, then it would blow all over the place in the wind, and then it would go all around the place. People would inhale it, and then they would get cancer and die, or all the other things that I talked about that you can get as a result of genetic damage exposure. And uranium is probably, in my opinion, uranium is certainly the most toxic of all the radiation hazards that there are. So some effort needs to be put, or some money needs to be put towards what I would say is a repackaging system.
I agree.
So the way I would do this, I would take each one of these things and I would leave it in its cylinder, but put that cylinder inside another cylinder. And then, make sure that all of them were repackaged like that into some really monstrously heavy, strong stainless steel cylinder. And then they were left exactly where they were, above ground. And the desire of the nuclear industry is to sort of like drop it into a hole in the ground and tiptoe away. But that's not the answer, because this stuff has a half-life of 4.9 billion years. So you really can't leave that sort of danger to future generations. Actually, the way things are going at the moment, I'm not so sure there will be any future generations after about 100 years.
Well, we might look different, given the mutations, to be honest. I've seen some of these cylinders, the depleted uranium cylinders, and one thing that troubles me, and one reason I actually got into this was just a first-hand, face-to-face observation of how these cylinders are stored. They're stored in open air without protection to the elements. They're rained on. Storms go through in and out of the Ohio Valley region in the U.S. They're not protected, and they're stacked usually 3 high. And given the amount of corrosion that occurs on these cylinders, what business do we have in regulating nuclear energy, NRC, stacking these cylinders on top of one another? That bothers me.
Well, I mean, I absolutely agree with you. I totally agree with you. The problem, of course, like everything else, is it comes back to money. I mean, the money has to be made available to package these things and stack them in such a way, you know, inside a hangar or something, but they'd have to be put in some way that they can be repackaged if necessary, or in fact it will be necessary at some point, but maybe hopefully quite a long time. But I mean, you have to say that the budget of the United States, because we're talking about the United States now,
yes.
the military budget of the United States, I understand this year or next year will be $750 billion. Okay, and so rather than making lots of missiles that you're never going to use, and in fact, in my opinion, you shouldn't be allowed to use or even make. What you should do is divert that money to making sure that these sites that we've been talking about, and it's not just a case of repackaging the uranium, there's all sorts of other things that are necessary. I mean, for instance, I'll give you one example. I did a court case some years ago about a site near Los Angeles called the Santa Susana Rocketdyne site in the Simi Valley, northwest of Los Angeles.
Yes, sir.
And what they did there, and that was another one of these highly contaminated sites. All sorts of buildings were completely rotten with radionuclides, mainly uranium, and they just blew them up. You know, they just dynamited them, knocked them down, and sort of shoveled it all up into holes in the ground and so on. And of course, all that time they were generating vast amount of dust, radioactive dust, which just blew all over Los Angeles and caused huge levels of cancer increase, including cancer in children, which is how I got into the case in the first place. And that's happening here as well. That's that's happening all over America. Yeah. These sites are falling to bits and slowly. Hang on a minute. What's going here? And slowly decaying. Hello?
Yeah, I'm here. It's interesting that you bring up the Santa Susana rocket site. As I live in Orange County, which is about an hour south of Los Angeles, and we had a wildfire, considered a wildfire, about 6 months ago, that originated. The actual site of origin was Santa Susana Rocket Research Laboratory. And we received smoke plumes over the Rocky Mountains over here, just going over Riverside over here into Orange County. And during that time, you know, I don't usually get very sick. I try to take care of myself pretty well. I had one of the worst respiratory issues that I've had in a long time by inhaling that smoke, and I hope that I don't have to suffer any long-term effects from inhaling that. But
well, the thing is, what would have happened there is that if that whole area up there is contaminated very badly, and so the plants up there will have taken up the contamination into the plants, just exactly what happened in Chernobyl. And so wildfires around Chernobyl, you can measure enormous increases in radioactivity in the air in the direction that the smoke from the fires around Chernobyl are directing or going. I mean, I've done a lot of work on those for the Russians, and certainly that would be the case in the Simi Valley as well. In that site there, that site is a very dangerous site.
Yeah. Yeah, that's just one thing that kind of troubles me, just because I'm so close to it. You know, I grew up in Metropolis. I don't want to go into that too much, but are you familiar with Metropolis?
Yes.
Okay.
I'm involved in a court case relating to Metropolis.
Yeah, righteous. Thank you. Highly appreciate that. That's where I'm from, though. But one question here is something that most.
Yeah, Metropolis is just another one of these. You see, I mean, they're all over the place. Unfortunately, they're all over the place. And what I want to do, what I hope to do, is if I can convince people, if I can convince everybody that the radiation risk model is wrong, then they will have to start realizing that these places are really not safe at all, and that the handouts that they get from the people who operate these plants, suggesting that there's no health problem associated with living nearby, is based on a load of bogus and dishonest science.
Yeah, and from what I've seen, just to touch on it, I can't really talk too much about it, but just the general vicinity of the population to the Metropolis plant is unbelievable. People live just across the street from the Metropolis plant.
Yeah.
That bugs me. Anyways.
Well, one thing that we're trying to do, that we're hoping to do, is to investigate that effect directly by looking at the cancer rates in the people who live there.
Yeah. Oh man. Yeah, we need to talk personally about some of this stuff. But have you? Just, to go back to some of the questions that I have, because I don't want to talk too much about like what's going on in the lawsuits right now. I kind of want to speak generally on the.
Well, I'm not allowed to talk about what's going on in the lawsuits. I'm just saying that there is one.
Yeah, awesome. Yeah, and I'm glad. But man, have you heard of what's known as sky shine?
No.
You heard of sky shine? Well, what it is?
Sky shine. Is sky shine? Is this you saying?
Sky shine. Yes.
Yeah. Well, I mean, I might know what that is.
How depleted uranium cylinders, when they're stored on a massive lot, how the neutrons actually bounce off of the clouds, and then travel throughout the community easier.
Well, I don't know quite what you mean there. I mean, there shouldn't be any neutrons associated with uranium particles just floating about the place.
Unless they've been introduced, right?
I seem to be losing your connection now.
Unless the neutrons have been introduced to the system.
I don't know. I'm not sure what you mean by that. There is a background level of neutrons in the environment, but it's quite low as a result of various cosmic phenomena, and neutrons can interact with uranium, but it's very, very rare to produce neptunium. Well, in the case of 235, produce neptunium 237. And then that can bump up again. Mm-hmm. But these neutron reactions are not very common, and they don't have at the level at which they operate. They don't have much in the way of implications for human health. The human health dangers from the uraniums are generally either alpha effects or else, if they're inside you, they're photoelectron effects. Those are the two main components of the health effects of uranium exposure.
Yeah, one thing I've noticed is that whomever's involved in the placement of these plants, they place these uranium plants, these radioactive processing plants near a body of water. Why?
Yeah, they have to do that.
Why do they do that?
Well, because they're chemical plants, and chemistry requires the use of water. You need water just for chemistry, apart from anything else, but you also need it for cooling. You need it for all sorts of systems. I mean, most factories need large amounts of water, but certainly any factory that involves chemistry needs enormous amounts of water for the chemical reactions to take place.
That makes it way
so
easier.
That's why they need rivers.
And it's much easier.
Well, of course, it uses vast amount of water, but also they've got somewhere to tip all the rubbish, That's the other thing. So if you go near any of these plants close to rivers, you find that there's enormous amounts of radioactivity in the sediment, and the fish are all dead. I mean, I've done a few of those as well, studies.
Yeah, it's just one thing I was going to say is, it's really convenient to place these uranium processing plants or uranium plants near a body of water because they use a lot of water. But also, it's convenient, extremely convenient, because they could easily dispose of waste into
they're not supposed to.
Outfall.
I mean, there are all sorts of laws about that. They're not, well, of course they probably do, and sometimes it's inevitable.
I know they do.
Yeah. Well, we know. I remember did a case down at a nuclear site in Florida, and it turned out, as a result of getting all sorts of information on disclosure, that they'd been, or maybe it was just a mistake, that they were just tipping their radioactivity down into the sewer. It wasn't being shipped out, and it wasn't, and these sorts of things, they do these sorts of things. They're a bunch of crooks, all of them. I mean, it's just a nightmare in the nuclear industry.
It is.
They're just all liars and crooks.
It is. Would you consider the nuclear industry to be the foremost corrupt and deadly league of individuals that ever existed on Earth?
Yes, no doubt about it, by several orders of magnitude. I mean, the contamination of the planet by radionuclides and the destruction and the effect that it's had on the human genome and the living system genome is the worst public health hazard of human history by far. And in fact, we've got a at the moment. Well, I mean, nobody can have avoided noticing the cancer epidemic. And the decrease in fertility, and all of those things are entirely a consequence of the flooding of the planet with radionuclides as a result of all the weapons tests in the 60s. It's just the feed-forward effect of that on genetic systems. And then, of course, on top of that, you've got all of the Chernobyls and Fukushimas and the various plants in the United States and other places like England, where these substances are just released routinely under license to the air and the water all the time.
Yes.
And what this has done is it's destroying life on Earth. No question.
Well, let's keep our eyes on this. I think definitely the releases to the air and the water is something we definitely need to keep watch of, and keep our eyes out for those documents that come out, and you do a little research. After a few years of research, you're going to start finding some really, really good information. All it takes is persistence and dedication. And Dr. Chris Busby, thank you for coming over to the U.S. from the UK. It's an honor to have you over here. Thank you very much for your service to humanity and the planet. And it's been an honor for me to be able to interview you. Thank you.
Yeah, you're very welcome. And it's good to have met you. Thanks a lot for having me.
You're very welcome. I look forward to talking to you in the future.
Okay, sure. That would be good. Bye then.
All right. We'll talk soon.